Right. So today's lesson is going to be about stoichiometry and limiting reactant calculations, which can be kind of tough. And the reason they're tough is because generally they deal with things that you've never seen before, like atoms and molecules and chemical reactions, which is something you've never actually seen on the scale that they actually work at. So it's actually a kind of a simple idea if you think about it with more everyday sorts of things. So let's say that we are in the car making factory, and we're putting together cars, and we're getting to the end of the day, and we're finding that we have 140 car bodies left, 520 tires, and 270 headlights. How many cars are we going to make before we're done for the day? Before we can't make any more cars, really. And when you think about it this way, this is kind of easy. Since there's one body on every car, I could make 140 more cars before I ran out of bodies. But since there's 4 tires on every car, I need to take the 520 tires and divide it by 4, and what does that end up being? About 130? About 130 cars before I run out of tires. And the 270 headlights will assume that I can get two headlights per car is going to be divided by 2 headlights per car. It gives me about 135 cars before I run out of headlights. So it turns out that I'm only making 130 cars. Now I have 140 car bodies, but it doesn't matter how many car bodies I have. If I'm out of tires or I'm out of headlights, I'm not making any more cars. So we're going to make 130 more cars before we run out. The tires in this case are what we call in chemistry the limiting reactant. They run out, and since you can't make cars without tires, you can't make cars. So it doesn't matter which ingredient you're missing. It wouldn't matter if I had 1,000 more car bodies. I'm out of tires, I can't make any more cars. The same thing happens in a chemical reaction. It's just that you're running out of a reactant, and so the reaction has to stop because one of the reactants is gone. And because that's so much more abstract, it's something you've never seen before, it can really be a tricky thing to do. So what we're going to do here is we're going to do a few examples, and we're going to have our examples all be things that happen at the family get-together in the summertime, the barbecue, the picnic. One of the things that I like to do at picnics is I like to grill. And when I grill, in the summertime anyway, because I've got lots of time, I'm a teacher, I'm not doing anything else during the summertime, I've got plenty of time to use a good old-fashioned charcoal grill. And so charcoal is just carbon, and it's burned in oxygen and changes into carbon dioxide. So this is the reaction that powers my charcoal grill. Now, what our question we want to ask here is if I take one charcoal briquette, I've kind of weighed and gotten an idea that they're about 85 grams for a charcoal briquette. And then we have a buttload of oxygen. Now, this is an important chemical term. It is very technical, scientific. In mathematics class, they have this term that they use for when you have a lot of something. You have more than you need. They say it's infinity. Infinity sounds kind of hoity-toity. Chemistry, we're more dealing with like the real world kinds of things on here. So we invented our own word, and the word is buttload. Buttload is the chemical version of infinity. It's chemistry infinity. So if we have got 85 grams of carbon and as much oxygen as we want, how many grams of carbon dioxide are we going to make? Well, in order to do this calculation, it's not really a limiting reactant problem because we know which one's going to run out first here, right? Determine which one's going to run out first. Well, you'd really hate to light up the charcoal grill and find out that the oxygen ran out before the charcoal did. I mean, we would sure hope that the carbon's going to run out first. You'd feel really bad, so it's a good thing. Make sure that you run outside, the next time your dad's lighting up the grill, run outside and say, "Dad, did you check?" And he says, "What?" "That the charcoal is going to be the limiting reactant," because you'd feel real bad if it turned out that the oxygen in the atmosphere was a limiting reactant and that you killed everybody because you wanted to have a cheeseburger. So anyway, so once you know what the limiting reactant is, and in this case, since we have a buttload of oxygen, that's not going to run out. The 85 grams of carbon is going to run out. We're going to start our calculation with the limiting reactant, with carbon. Now, think about your mole maps here that we've been talking about. If we think about what we're trying to do here, we're starting off in carbon. So we'll call this island right here, this is Carbon Island, the top island is. And we want to get our answer into how many grams of carbon dioxide are we going to make. That's the answer that we're looking for. So we're trying to go from carbon into carbon dioxide. Now, we happen to be in the mass area of, we're right here, we're in mass of carbon, and we want to get into a mass of carbon dioxide. That's what our answers being asked. That's what we're being asked to give. So what we're going to do is we're going to go to moles of carbon, then across the mole ratio bridge into carbon dioxide, and then to a mass of carbon dioxide. So that's our plan of attack. It's a good idea to get a plan for your calculation before you begin. So follow along here. We are in 85 grams. That's our charcoal briquette. If we have 85-gram charcoal briquette, in order to get it into moles, we need to use the molar mass. And we look on our periodic table and find that carbon is 12.001 grams per mole. So we cancel our grams, and now we are into moles of carbon. Okay. Now going back and looking at our chemical reaction, it's one carbon reacts with one oxygen to form one carbon dioxide. It's a 1-to-1-to-1 kind of reaction, very simple. So that means that for every 1 gram of, for every 1 mole of carbon, I create 1 mole of carbon dioxide, and so I can cross the mole ratio bridge, and now I'm on the carbon dioxide island because my units are now being listed as carbon dioxide. And now that I know how many moles of carbon dioxide I have, I'm going to take and I'm going to use the molar mass of carbon dioxide. I add up 1 carbon and 2 oxygens, and I get 44.01 grams of carbon dioxide. And I'll be into a mass of carbon dioxide. My calculation is done, and when I crank that guy out, I get 311 grams of carbon dioxide. Okay, so that's a fairly straightforward stoichiometry problem. It's not really a limiting reactant problem, since we were told we had an excess of oxygen, a buttload, more than we were going to need of oxygen. But you know, sometimes during the school year, I don't have time to light up the charcoal grill. The charcoal grill, like you can actually run an actual charcoal grill, takes like a long time to get the charcoal cooking, and then it's actually better once you get it going, but it takes forever. So sometimes during the school year I don't have time, so I bust out the propane grill. So let's take this propane right here, C3H8, and when we burn this in oxygen, it takes 5 oxygens for every 1 propane, 5 oxygen molecules for every 1 propane molecule, or 5 moles for every 1 mole of propane, depending on how you want to look at this. Then we create 3 moles of carbon dioxide and 4 moles of water. And if we burned an entire 30-pound tank, 13,620 grams of propane, that's the whole tank. Let's say we blew it up on accident, or we just left the gas grill on outside overnight, forgot to turn it off, and it all burned out, whichever story you like better. If we used it all up, how many grams of oxygen are we going to suck out of the atmosphere? So the question here is, how much oxygen is going to be drawn out of the air in burning the 13,620 grams of propane? Okay. Again, first thing we want to do here is determine if we have a limiting reactant problem. And since it's not really asking us, it's not giving us 2 reactants, it's giving us 1 reactant and saying how much of the other one do we need. We pretty much are trying to figure out what's the perfect amount, what we call the stoichiometric amount of the other reactants, so that we have a perfect reaction here where both of them are used up. Okay, so there's not really a limiting reactant in this particular problem. So what we're going to do here is we're going to start with the reactant that we know about, which is going to be the mass of propane. And we are going to try and change this into a mass of oxygen, which is what the question is asking us to get to. So we're starting off the island that we're starting off on is propane island, and we're trying to go to oxygen. And so we're going to use the ratio of 1 to 5 for our mole ratio there between propane and oxygen when we do this. We're going to go into moles of propane, then cross into moles of oxygen, and finally into a mass of oxygen. It's really pretty much the same calculation as the previous one, only we're going to do it with a different mole ratio this time and with different compounds, I guess. So we start off with our mass of propane and change it into moles. There's 44.1 grams of propane in 1 mole. And then we are in moles of propane. We're going to use the mole ratio of 1 mole of propane reacts with 5 moles of oxygen from our chemical reaction. We got that information. The coefficients there tell us that it's a 1 to 5 ratio. So now we are in moles of oxygen, and finally we go into mass of oxygen by using the molar mass of O2, which is 32 grams per mole. And we calculate this out, and it turns out that in burning a whole tank of propane, you use 49,410 grams, that's about 50 kilograms, 120 pounds or so of oxygen out of the atmosphere. The other thing we like to do at Peterson gatherings, I like to be the bad uncle or the bad cousin who takes the little kids aside and is like, "Hey, little kid, does your mom have vinegar and baking soda?" Yeah, let's make a volcano, and like we use up all the vinegar and baking soda at the mom's house. And so what we do here is we take and into the volcano there. What if we had like all we could scrounge up from around the house was this is the sodium bicarbonate is baking soda, and the acetic acid there is vinegar. Let's say we want to figure out how much gas we can create, and all we can scrounge up around the house is 100 grams of each of those things. Okay. Now this is where we have to put on the big boy pants. Like this is tough. Since we have 100 grams of each, and since a gram of baking soda contains one amount of particles, and a gram of vinegar contains a different amount of particles because the particles don't weigh the same, you can't just say, oh, there's an equal amount of each. Look, it's a 1-to-1 ratio, and we have a 1-to-1 ratio of reactants. We can put it. No, this is complicated. What we need to do here is when we mix those together, we need to figure out which one's going to run out first. It's not going to be cute, okay? So in order to figure out which one's going to run out first, what you have to do in a limiting reactant problem is if they're given to you in masses, you have to convert them into moles and compare moles. We can't compare masses. I can see from looking at this reaction here that it is a 1-to-1 reaction. However, that doesn't mean that I need 100 grams of baking soda and 100 grams of vinegar is going to be nice and cute, because again, a particle of baking soda doesn't weigh the same as a particle of vinegar, so we're going to have a problem here. Convert both quantities to moles, and then we can compare the quantities more accurately. So I take my 100 grams of baking soda and I change it into moles using the molar mass, which I've found by adding them up off my periodic table. And it turns out I've got 1.19 moles of baking soda. I do the same thing with the vinegar, using the molar mass for vinegar, of course, not molar mass for baking soda. And I get 1.67 moles of vinegar. Okay. Now, the next step is you need to compare those numbers using the chemical reaction. So we have our chemical reaction written here, and we have our numbers. Amount of baking soda and our amount of vinegar, the moles, we need to compare them and figure out which one's going to run out first. Okay? We have 1.19 moles of baking soda and 1.67 moles of vinegar. Now, this is a limiting reactant problem, and it's difficult, but it's about the easiest limiting reactant problem that you can possibly do. We're trying to start you off easy here. Since this is a 1-to-1 kind of ratio, it's a simple matter of looking at this and figuring out whichever one's got fewer moles is going to run out first. And when that runs out, the reaction is going to stop. So it's easy to say that in this particular case that the sodium bicarbonate, the baking soda, is going to run out first because it's a 1-to-1 ratio, so the one with fewer moles is going to run out. Okay? So the sodium bicarbonate is the limiting reactant. So now what we're going to do is we're going to do the calculation to find out how much CO2 we can make before we run out of sodium bicarbonate, because that's what's going to run out first. So our calculation is going to start off, since we just figured out how many moles of sodium bicarbonate we had, we started off with 100 grams of sodium bicarbonate, but then we converted it into moles to compare it to the vinegar. So since we already know that we had what I think was 1.19 moles of vinegar, we might as well start off in moles here rather than going back and starting here in mass. But if you want to do extra work, feel free. So the 1.19 moles of baking soda should be converted into moles of carbon dioxide. And then we're going to change it into a mass of carbon dioxide, and that will be our plan for this problem. So we're going to go across mole bridge into moles of carbon dioxide. It's a 1-to-1 ratio between the baking soda and the carbon dioxide, so we can use a 1-to-1 mole ratio. And then basically once I'm in moles of carbon dioxide, I've got this thing pretty much licked, use the molar mass of carbon dioxide, and we're home free here. So at the end of this calculation, it turns out that from mixing 100 grams of baking soda and 100 grams of vinegar, I get 52.8 grams of carbon dioxide. Okay? Now, the other question that will sometimes jump up and say, hey kid, you're pretty smart if you figured that out. What about this? We'll say, what's the mass of the excess reactant? So it turns out, remember that we said baking soda was going to run out first here. So that means that there's going to be some extra vinegar left over. The question here is how much extra vinegar is left when everything's said and done. So, well, in this problem, again, it's the simplest limiting reactant problem I could probably give you. This question isn't so tough. Since it's a 1-to-1 ratio, and if I use up all of my 1.19 moles of baking soda, that means I'm going to use up 1.19 moles of the vinegar as well. And if I started with 1.67, It does not take a mathematical genius to subtract out the 1.19 moles that were used up from the 1.67 moles I started with and end up with 0.48 moles of excess vinegar left over. And if you know how many moles you have and you'd like to report that in grams, then you just use the molar mass of vinegar. So if I had 0.48 moles left over at 60.05 grams per mole, I would have 28.82 grams of extra vinegar. This abbreviation here, XS, is something that I've sometimes confused students with in the past. XS is the same thing. It's a shorthand for the word excess, which means extra. So that's how much extra vinegar there is left over. So once the baking soda and vinegar stop reacting, the baking soda runs out because it's a limiting reactant, and there'll be 28.82 grams of extra vinegar left.